hopefully all of you on the old stream that I just killed show up here momentarily. I don't know if it was buffering on my end or on your end. I can see that some of you are starting to show up. I'm so sorry that I had to dash, but I think maybe this stream will be better. We're gonna all find out together. Looks like most of you are making your way here. I would like to, again, apologize if it's buffering really bad. Everyone I know has Wi-Fi struggles, myself and yourselves included. So, I wonder if this, turn that off. Okay, we're gonna give this a go. I can see a few more of you trickling in. Again, I'm really sorry about the buffering. Hopefully it won't be that bad. Yes, it's working better. Yeah, you know what? Technical difficulties, I don't want to say they're my life, but maybe it was just a glitchy moment. I don't know. But hopefully this will work. I turned off the Wi-Fi on everything else I own. Oh, perfect. I'm glad it's working. Okay. Let's very briefly, I will tell you a little bit more about the quip, which is really, if you've already heard it before, it's the same thing, but now with maybe less glitching. So the quip opens at 4:15. The screen was purple. Y'all, the struggle is real. Okay, so your quip opens at 4:15. In the, like when you sign into the quip, all of the directions will be in there. There is no time limit. So you have until 11:59 to do it. You can email it to me if you cannot get it to work. So you should be able to upload a PDF. You can download Cam Scanner, which is free. There's a way. I own an iPhone, so I know how to do it on my iPhone. In the Notes app, you can basically say, make a PDF. It'll take a picture. You can upload that. You can take a picture and upload that. The only downside is for the exams, which is what we're going to try to figure out how to do, you will have to upload more than one picture, and there's only going to be one file upload place. So you need a way how to take more than one picture and put it in there. Okay. For the exam, which is in 2 weeks, so it is my intent, based on how this quip goes, to give you some information about exam 3 today, and then more information about it next week. And I will host a separate Zoom session that's basically so you can pop in and ask any questions you have other than office hours. So we'll figure that out. Okay. Any other questions before we start talking about the next part of chapter 8? Okay. Sorry, working on finding my notes. So today, if you are looking along in the slides, we're starting on slide 9, where we're going to talk about bonds. Bond polarity and the last periodic trend, which is electronegativity. You're fine, Lo. So in section 8.4, we want to talk about bond polarity and electronegativity. So we talked about, so on Monday, we talked about how you can have an ionic bond where they don't share, and in a covalent bond, we do share. But it turns out that there are two types of bonds, which is a measure of how well we'll say how well two elements share electrons. Yeah. So one thing we know about sharing is you can be good at sharing or you can be bad at sharing. So when we think about electrons, I tend to picture two atoms sharing a blanket. Now, a blanket sharing can be both of you have the equal amount of blanket. One person can be a blanket hog where they basically turn into a burrito and you have none. Or there's some sort of one person kind of takes most of the blanket, but not all of it. So we have a nonpolar covalent. Electrons are equally shared. So in a nonpolar bond, everybody has the same amount of electron density. So that's one type. So this, we'll call it one. For covalent, so if we think about nonpolar being equally shared, polar covalent is going to be unequally shared. So electrons are unequally shared. So it's worth remembering that the third option is an ionic bond. And we talked about that in section 8.2. And in an ionic bond, there is no sharing. So in an ionic bond, this is a metal nonmetal, and you have one cation and one anion, where these are going to have a bond. Okay. So if we want to figure out how well an electron can or cannot share, we're going to use electronegativity. But I know that if I start erasing, you guys will not be ready. So I'll start talking and then we'll go back. So we're going to use this last periodic trend titled electronegativity in order to determine whether or not a bond fits into one of these three categories. So electronegativity is the ability of an atom in a molecule to attract electrons. So electronegativity is a measure kind of like electron affinity or ionization energy, where we can measure how much the atom in a molecule wants to hoard all of the electrons. So in this way, we can kind of try to figure out how that works. Okay. I know, honey. Sorry, I woke the dog up. Well, yes, I did do that. You're okay. So we can determine the electronegativity. So the electronegativity scale was developed by Pauling, a super famous scientist. So one of the things that Pauling did is he realized that electronegativity combines all of the periodic trends that we learned in the last chapter. So all of these, they all go into a bucket, you shake them up, and out comes electronegativity. So if you move to slide 10, you can see the electronegativity scale. So in this case, so it's often an absolute value, so it doesn't have like a negative charge or a positive charge, but electronegativity values, it ranges from 0.7 all the way to 4.0. So the larger the number, the more electronegative it is. So if we look at our periodic table, okay, it increases in this direction. So fluorine is the highest, and cesium, which is down here, is the lowest. So when we think about the electronegativity trend, we can use that to ascertain or determine whether or not atoms are, or in a molecule, are going to be polar or nonpolar. So to determine the electronegativity, so to determine the electronegativity of a bond, we subtract the electronegativity values. So electronegativity is usually called chi. So chi, or this fancy X, is electronegativity. So what we can do in this case is use the electronegativity to determine whether or not a bond is polar. So if we subtract chi1 minus chi2, where these are any elements anywhere. So if it's equal to 0 to roughly 0.5, that is nonpolar. From 0.5, no, that's right. Yep, 0.5. This, like 2.5, these are going to be polar molecules. And 2.5 all the way to 4.0, this is going to be ionic. Now, likely, your other question is, so do we have to memorize the electronegativity series? No. But we can use the trend that basically says the further apart two non-metal atoms are, the more likely they are to be polar. If the bond uses one of the halogens that is low in molecular weight, fluorine, chlorine, and bromine, it's probably going to be a covalent bond, a polar bond. Ionic bonds are anything with a non-metal metal, so they're always going to be ionic, never anything else. Non-polar always happens if it's the same element or elements that are really close to each other, like carbon and nitrogen is non-polar, but carbon and oxygen is polar. So if we look at slide 11, which I'm going to do my best to draw. So if we think about electron density, or two atoms that are the same, that's not F2. We can see, supposedly, that these are the same electron density, meaning they're the same shape. So if we also look at HF, where this is our hydrogen and this is our fluorine, we can see the reason it looks lumpy is not just because there's difference in size, but instead what we have here is that the electron from the hydrogen is pulled towards the fluorine. So fluorine is the most electronegative, and it hoards pretty much all of the electron density all of the time. So, but it's the same element, so it matters who it's connected to. The last is the lithium fluoride, which looks mostly the same as this one, but it should look more dramatic. I just ran out of space. So in the ionic bond, there's almost no electron density left around the lithium. So the question is, whoops, sorry. How do we think about this information and what does it mean? So you're okay. So when we think about HF, the electronegativity scale, 4.0, erase that, minus the hydrogen one, which is 2.1, gives us 1.9. So this is a polar bond, okay? So we're gonna take our, so this part, in my opinion, says, it indicates the positive end. And the arrow points to where the electrons go. Yeah, I think you're gonna just have to refresh it. You can also back up and I will repeat this. So this arrow here is for polarity. So the positive end indicates the positive side of your bond. Then hopefully that helps with some of our clarifications. So if you wanted to get technical, and if you look at slide 12, we could start to, we can calculate how much of this is moving in either direction. So we can calculate polarity. So we can determine what's called the dipole. So that thing that I just drew, the molecule that looks like this tells you about the electrons being shoved in one direction. We can calculate how big or small this arrow is. And we can calculate the dipole moment. And we can use this equation. Mu equals QR, where mu is the dipole moment. Q is the charge, and R is the bond length. So you could imagine that the further apart they are, the smaller the dipole is going to be. The bigger the charge, which basically tells you how separate these two are. So if it is something that is only slightly polar, the dipole will be smaller. So I'll write this here, not on exam. That also means it's not on the final. What is R? R is the bond length. So R is how far apart they are. So if you look at slide 13, and I will draw some of these up here or give you the info in case you don't have the slides. So when we think about the bond length versus the electronegativity, so if we look at HF, HCl, and HI, so the bond length for HF is 0.92 angstroms, HCl is 1.27, and HI is 1.61. So we can see based on these, which isn't surprising, because we know that as you go down the periodic table, they get bigger. So here's our bond length. We also know that we can think about the electronegativity difference. So the chi difference is 1.9, 0.9, and 0.4. We can also see that the dipole, based on these, we expect there to be almost no dipole here, but a higher dipole here. Basically, it tells you how much the sharing is happening. Yes, the electronegativity values, if you need them, will be provided, or the way for you to calculate all of this. This is on slide 13, and anything you needed off of that slide would be provided on the exam. So it's 1.82, 1.08, and 0.44. So basically, the further apart they get, and the lower the electronegativity difference is, then this would be the dipole moment gets smaller. So dipoles tell us about how far the electrons are pushed to one side or pulled to a different side. And so that is super important, but not necessarily something that we have to have all of the time. So, Sebastian, the dipole moment is calculated chi equal, no, it's not. Mu equals QR, where mu is the dipole moment, Q is the charge, R is the radius. There's a bunch of conversions in here, which we're not going to talk about this semester. So the next thing we want to talk about is probably, I don't want to say, start to talk about probably the last difficult topic for the semester. That's right, the whole semester. So we're going to use the information about Lewis dot structures for atoms to try to take, bye Ronnie, we're going to take time to think about how to make them into molecules. So in section 8.5, and for the rest, you do not need to use the electronegativity in order to calculate this. The bond length is R. The charge is usually calculated in a different way. And if you're super curious, I'm happy to show you how to do it in office hours. But for the next several sections, we're going to talk about how to draw Lewis dot structures for not small molecules, not methanes, more like complex things. So in 8.5, we're going to talk about how to draw Lewis dot structures. Oh my gosh. So Lewis dot structures for molecules are relatively simple, but there are some guidelines. So I'm going to read them, skim them, but it will be best for you if you can pull it up on slide 15. So it says the guidelines. 1, sum all of the valence electrons. Make sure you take into account the molecular charge. 2, write the symbols for the atoms connecting with adjacent atoms with a single bond. Okay, so far so good. 3, complete octet around all atoms connected to the neutral electrons. 2, write the symbols connecting adjacent atoms with single bonds. 3, complete octet. For outer elements. 4, put remaining electrons on central atom. And the last step is, whoops, not number 4 again, number 5 is use multiple bonds if central atom, now, whoops, I need my face to be to the side, so if you're copying along, you can. The thing with step number 5, it sounds like we're gonna encounter this often. To me, it's the equivalent of a 90s kid being told to stop, drop, and roll. Look, I'll be honest. I always knew that I should stop, drop, and roll. As a child, I was pretty sure that I would be encountering some reason for that. In Gen Chem 1, this does not happen all that often, but it will happen some. So most of the time, by the time we get to step 4, we'll be done. Step 5 only happens under certain conditions in the types of molecules that we're going to talk about. So the first thing we want to do is I'm going to erase all this so that we can. So let's look at PCl3. So if you remember last class, one of the things I often said was I'll underline the central atom. And you were like, okay, why is it underlined? It tells you how to connect the elements, which is a really important part. The rest of number 5 said to put the use multiple bonds if there aren't enough to make octet for the central atom. Sorry about that. It's also on slide 15 on Canvas. So we're also going to look at HCN, where carbon is going to be the central atom. So the first step is to calculate our valence electrons. So I always write hashtag VE or £, or number sign, whichever way you would think about it, the number of valence electrons. So the thing that we have to think about is how do we determine the number of valence electrons? It comes directly out of the periodic table, where we have 5 plus 3 times 7, which gives us 26. Hey, how blurry is blurry? Like I need to write bigger, or it's so blurry you can't see what's happening at all? Y'all, today our technical difficulties are going to get us. So if you're not reading the comments because you're on your phone, a couple of people have recommended to change the quality to 480 or 720. Sarah, I'm going to go right back over where those numbers came from, so hang just a second. Oh, it looks like everything's working. Huh, super news. I will try to include that in my Friday update, just some hints and tips, and we'll go from there. So let's go back to where we were. I'm also going to try to write way bigger. Also, it's not news to me, but I didn't realize you couldn't quite see what was at the top. Okay. So this is phosphorus trichloride. So the first thing we want to do is determine the number of valence electrons. So # VE is just Dr. Malcolm shorthand for like How many valence electrons? We are on 15, between 15 and 16. We're just going to do some examples so that if you want to look at your slides, I would look at 15, and we're going to go through those steps for 2 different molecules. So the valence electrons come off of your periodic table. Now, I know you can't see this really well, but here we go. The number of valence electrons is 1 here, 2. Transition metals do not have valence electrons. Don't try to find those. From here across, come on, table. 3, carbon has 4, 5, 6, 7, 8. Rows 1 through 8, if you remember it, like on the green sheet, if you still have it, at the top it says 1 through 8. That's how many valence electrons you have. For everything in that column, they are the exact same. So we know that there's 5 for phosphorus and 3 times 7 for chlorine, which gives us 26. Now, you don't necessarily have to do this, but this helps with the later steps on that. So the reason phosphorus is underlined is because it is the central atom. So we're going to put our phosphorus in the middle, and we're going to connect our 3 chlorine molecules on any side. Okay, I'm going to have to erase this a little bit, make it smaller, otherwise you're going to run out of space. So from here, the goal is to figure out where else the valence electrons go. So we have 26 of them. The second step, one of the next steps. So we've done step 1. We have 26 electrons. The second thing we're going to do is we're going to draw a molecule. Central atom is underlined. Everything else, unless otherwise indicated, is connected to the central atom. Now we have to use up our electrons. So we need to use 26 electrons. But we have to count as we go. So I tend to count by 2. Electrons come in pairs, right? So nobody is lonely, at least in this section. Sometimes they are, but not usually. So each of these bonds is 2 electrons, right? Because 2 electrons makes a bond. So we're going to start by adding octet on all of our exterior atoms. 1, 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh man, I lost count. Hold on. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So the goal is to make octet for everybody on the exterior. So we did. We've used 24 of 26 electrons. Now we're going to add the last 2 onto our phosphorus up here. You'll notice that we're still using Lewis dot structures where they're all separated by 90 degrees. So now we've used 26. It's always a good idea to just double check. Does everybody have octet? Because that's really important. So octet means that there are 8 electrons around each one. 2, 4, 6, 8. Good news for chlorine, they all look the same. For phosphorus, 2, 4, 6, 8. Phosphorus looks good too. So this is the Lewis dot structure for PCl3. So I'm going to give you guys a second. I'm going to have a sip of coffee. That way you have a chance to draw this. I think part of the problem is I'm trying to put too much stuff on the slide. So I will go ahead and erase it and start with HCN. Next. If you would like something to kind of think about, you can look at, I'm trying to think of another example. Natalia, that is correct. Outer first and then the central. You can look at, if you would like to, like the 3 I'm going to do are this one, and then, yeah, we'll do that one. BrO3 minus. if you want to, give it your own go before I erase this and keep going. Okay. Let me underline that. So for HCN, step number 1, how many carbon has 4, nitrogen has 5. Now, if it's 3 elements in a row, usually they're written in the order that you read them. I will always try to underline it. It is, I don't want to say even more so now, but I never want to trick you. That is definitely not the plan. So that's not our game plan. So we connect these. Now we have 10 valence electrons. We've connected our hydrogen, carbon, and nitrogen all in a row. I might make it a little bit better. Maybe not. We'll find out. I have no idea what those brackets mean, Megan. So with HCN, we have hydrogen, then carbon, then nitrogen. So the directions tell us to, why don't you multiply by 2? So you multiply only if you have more than 1. I'm glad it was your cat. I thought it was a joke, and I was like, I don't get it. So we multiply by 2 or anything else if there's more than one of those elements. Otherwise, everybody just uses their same. So from here, we've used up to 4 of our electrons, so we have 6 left. So it tells us to put them on the outer atoms. Now, you might have wondered, why doesn't hydrogen get any? So hydrogen is a 1s element. The s orbital can only hold 2 electrons. So the octet for hydrogen, in fact, is 2 electrons. So this has octet. Nitrogen has 8 electrons around it, but carbon only has 4, and it needs to have 8. So it turns out that we can make double bonds, or in this case, a triple bond, by moving these electrons here. So our real structure would look like this. So when we do this, this triple bond allows both carbon and nitrogen to have octet. So their carbon has 2, 4, 6, 8 electrons. Nitrogen has 2, 4, 6, 8 electrons as well. So like I said before, the ability to put extra electrons around the central atom only really happens when you have nitrogen, carbon, occasionally sulfur, and oxygen. Anything that's a halogen doesn't make double bonds. So from here, we're going to look at BrO3 minus. So Sam, is your question about why I did this? Well, I'm going to assume that it is impossible, but hydrogen here only has 2 electrons, makes octet. So two electrons, yeah, we can see that. 2 electrons is octet for hydrogen. And so our goal, if we left it like this, carbon would only have 4 electrons around it, and that is not octet. So we want to make octet. And maybe today, for sure on Monday, probably Monday, we're going to talk about all of the elements that, like everything else, violate octet. The bond is equal to 2, and 2 is the component for hydrogen, yes. Every bond is 2 electrons, so 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Glad to help. So next, let's think about BrO3 minus. What do I do with my eraser? So the number of valence electrons for BrO3 minus is going to be a little different. So we'll have 7 for bromine plus 3 times 6 for the oxygen. So we multiply by 3 because there are 3 of them. Then we have to account for this negative charge. It's kind of like when you have a plus or a minus here, it either takes or adds a valence electron. So when we add that in, 18, 19. So we have 26 valence electrons. So from here, we can start to do all of the same rules. We're going to connect them together. And then we've used 6 electrons, so we're going to start putting our extra electrons all the way around. So now we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 of 26. Here, this molecule has a negative charge. So today, what we can do, and by today, I mean like for the next 12 seconds. So you can't always just put brackets and then a negative charge. This tells you that we don't know who has the negative charge. So it turns out that in Lewis dot structures, we want to be able to calculate formal charge. So formal charge it assigns, we can do the charge to 1 or more atoms. Yeah, we can see that. So the next thing, sorry, I'm trying to be in the screen but not block this. The next thing we want to do is determine the formal charge for this molecule. We know that it has an overall negative charge. The question is, who has the negative charge? Either who one person or who multiple people has this charge. So if you look at slide 16, we want to calculate the formal charge for an element. So formal charge is a relatively simple calculation. Now, I'm going to show you one way. There is another way. It is the Alex preferred method. Both of them are 100% correct. So formal charge, we have to assign the electrons. So to calculate the formal charge, or I tend to write FC, so formal charge is equal to the number of valence electrons minus half the bond electrons, E minus lone pair, E minus. Now, this is super hard to read. So what I'm trying to say is for oxygen, if we want to calculate the formal charge for oxygen is going to be 6, which is the valence electrons, minus how many electrons are in a bond? 2 electrons are in a bond. So oxygen and bromine are going to divide this in half. So oxygen gets half of this bond of electrons. So there are 2 electrons in the bond, they get 1. So 6 minus half of 2 minus all of their lone pair electrons, 2, 4, 6, gives you -1. Now, this is for oxygen. So that tells us, based on this calculation, that oxygen has a negative charge. Now, this oxygen and this oxygen look identical to all of these. You can calculate the formal charge for all of them. However, if they have the identical structure, they're all going to have the same charge. So now all three of our valence electrons for bromine are 7, minus half of the 2, 4, 6 bonding electrons, so 3, minus 2, so 7 minus 3 minus 2, that gives us +2. So on slide talks about identifying the dominant Lewis dot structure. So in that case, so this is the dominant structure. You could try to make some other things, but it violates a lot of other rules. So we want the formal charge to be closest to 0, and we want the negative charge to be on the most electronegative atom. In this case, that is true. So both of the oxygens, or all three of them, are more electronegative than bromine, even though bromine is often considered an electronegative atom. So now we're going to look at a couple of examples, which I will do one, and then we'll talk a little bit about resonant structures. I know that it feels like we're not doing very many examples today. I'll try to post a few more videos of that. But the other thing is we are going to draw Lewis dot structures every day between now and the exam. So right now, you kind of want to start thinking about how to follow the rules and start to learn the rules. We're going to draw so many Lewis dot structures. For the exam, it's going to get easier. So, right, the big bracket is only for if you don't know where the negative charge is. But as soon as you know where it is, using a Lewis dot structure, we don't need it anymore. So let's look at NO2 minus. Back there. NO2 minus. So for NO2 minus, nitrogen will be the center atom. And we know that nitrogen has 5 valence electrons plus 2 times 6 plus 1. That gives you 18 valence electrons. So in this case, once we start to think about NO2 minus, we know there's going to be a negative charge. We also need to think about where the electron's going to go. So we'll start here. So now we've used 16 of our 18 valence electrons. So the last 2 go on nitrogen. Now, this becomes a little bit more complicated because NO2 minus, nitrogen doesn't have octet yet. So we know that this can't be our preferred structure. We have to have octet around all of the atoms until we learn about the ones that don't have octet. So when we have less than octet around a central atom, we want to take one of the lone pairs for an exterior atom and share with the central atom. So here, now we have 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around nitrogen, 2, 4, 6, 8 around the other oxygen. Now you might be a little curious as to why I picked this side, because it was next to me. You could have chosen the other side. In a second, we're going to talk about that some more, because that's going to create something called a resonant structure. But first, let's calculate the formal charge for this molecule. So Because we have two different ones, I labeled them in ways that you cannot see, so we will get some colored markers so you can see that. The oxygen with the red bubble next to it, and the one with the blue. This is just going to allow you in the video to see the difference between the two for the formal charge calculation. So the formal charge for red oxygen is going to be 6 valence electrons minus half of 2 minus 2 for 6 electrons, and that gives you -1. Okay, that's great. But what about the formal charge for the nitrogen and the formal charge for the blue oxygen? Because we always want to make sure, just because we found a negative charge, well, what if there's more than one? So for nitrogen, there are 5 valence electrons minus half of 2, 4, 6 minus 2. So the nitrogen, sorry, I kicked it off. You're all right. So the nitrogen does not have a formal charge. Sorry, Lo. For the oxygen that's blue, we again have 6 valence electrons. It's not working. Minus half of 4 bonding electrons minus 4 lone pairs. So this also has a 0 formal charge. So now we know that the formal charge is located on this atom. So the next slides start to talk about something called resonance. Resonance is the ability to have more than one equivalent structure. I'm going to let you guys keep writing before I start erasing. Yes, Allie. So the 6 for nitrogen here came from all of the bonds connected to it. Is okay. So resonance is more than one equivalent, meaning the same structure. So if I'd been on the other side of the board, I probably would have drawn the double bond next to the red. But I was on this side, so that's why I picked it. But one of the things we think about is, okay, well, these look totally different. But they look different because I drew them differently. Resonance tells us that these two structures are the same. So the molecule switches back and forth between these rapidly, instantaneously. So if you were to stop the electrons, if you were to take a picture, you should look and you should hopefully find either option A or option B. So it turns out that resonance is a little different. So a resonance tells you that there's more than one bond order, single bonds versus double bonds. Single bonds are longer than double bonds. So the question that people often ask is, well, if you stop it, shouldn't you see a long bond and a short bond? It turns out that what we see are two same bonds. So a composite structure which composite just means like an overlay something together, would be this. having one single and one double, we get two 1.5 bonds. So the bond length is an average of what you see. Whoa, no, you can see that. So if you have a single and a double, in this case, in your composite, you would have a 1.5. In composite structures, you would also draw them with a bracketed negative charge because the negative charge is over both sides instead of just one or the other. So resonant structures are the ability to create more than one equivalent structure. So we also, I don't want to erase because I know you guys are working along. We'll look at ozone. So O3, where all three of the oxygens are connected. So I'm going to go ahead and erase this, but I won't erase this just yet. So ozone is three oxygens connected together. So we're going to have 18 valence electrons. That's where we end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, one of the things you're going to start to notice is that when you see this pattern over and over again, you're going to start to know, like, okay, when oxygen looks like that, it has a negative charge. When it doesn't, we get a positive charge. Positive is really rare. But in this case, we know that this uses all of them. This, however, does not have octet. I'm going to give it octet. So I was asked, in the past, you said that the electrons should mirror one another. So why is it 2 electrons on top in the central instead of 1 on top and 1 on the bottom? It's a good question. So lone pair electrons always come as a pair. So in this case, in any time we draw a Lewis dot structure, we don't tend to have single electrons. So the expression 1 is the loneliest number is super true for electrons. So electrons are almost never found alone. We almost always find them as a pair, regardless of component. Oh, good. That's great. Glad to help. Sorry you had to run away to come back. So that is why that is. So in this case, we would see almost the identical resonance structure as we saw before. So we see it a lot in carbon molecules or upper level organics. So I'm going to hang out here for a second because it's 4:15. So what I want you to do, not like it's homework, but as practice. So, period. That's like not a word. No one can see that. So for practice, if you would like some, you could try CHCl3. So carbon with 1 hydrogen, 3 chlorines. One second. What about H2O with oxygen being in the middle and SO3 2 minus with sulfur being the central atom. Okay. Oh, Sarah, for the formal charges with ozone, which looks like this. No one can see those dots because the video is bad. So the formal charge for this oxygen is 6 minus half of 2 minus 6, and so that is -1. This one is 6 minus half of 4 minus 4, so that's 0. This one here is 6 minus half of 6 minus 2, just +1. So I think I just skipped ahead because I was a little concerned about time. So here are a couple of practice problems. If you would like to do those this weekend, they are not essential. We will continue to do more practice problems on this. Anyone have any other questions? Don't forget to do your quip tonight. It's due by midnight. Email me if you have problems. Pop into office hours. If you cannot figure out how to do it, I will help you. This is the only quip where I will basically help you do everything about it. I'm happy to help. I hope you guys have a great weekend. Staying inside your house, doing a whole lot of Netflixing. Miss you guys. I will see you next week. Or in office hours. Feel free to go to SI. I'm pretty sure Megan's going to do lots more examples.